Hello everyone, and welcome to this talk about cryptography. We are live from Paris right now. Today is Monday, 13th of September. I think you're watching this on Friday maybe. So I'm very happy to be giving this talk for Sogeti Labs. I've been part of the community since 2019. And don't worry if you don't know about cryptography. If you already have a tech background, a bit of coding, it would be ideal. But otherwise, I'm gonna present everything kind of from scratch. So let's get started. Okay, so well, a word about me. So I'm the head of cybersecurity research and development for Sogeti in France. And I've also founded a company called H25 in France, which organizes challenges, so coding and cybersecurity challenges mainly. I also do some artificial intelligence. In a nutshell, I love everything that's technical that involves coding. I'm a big Python fan as well. And right now I work on cybersecurity and mostly about popularization of some concepts such as cryptography, which I love. So we are gonna have a look at four major events that have paved the way of cryptography as it is today, that have affected maybe not our daily lives, but have been kind of a big deal in that world and have had an impact on the technical world and the cybersecurity world as a whole in the last decade. So to begin with, cryptography is already solved. Mathematically, it's if you ignore quantum technology, which is kind of a big deal actually. In theory, cryptography, it's kind of a done deal. Well, we always try to improve, but that's about it. We already found concepts and crypto systems that are secure enough to be secure and make any communication unbreakable. But sadly, there are still issues in the real world. Main issues being implementation, so how we code the solutions that have been designed by great mathematicians. Bad usage, we can have a great system but use it very badly and make it really inefficient and really broken. And key safety, so how you keep the keys is also very important, but that's not part of cryptography. It's more general computer security. One main thing is also that a cryptographic failure can go unnoticed. So if you there sometimes for example, the communication can be intercepted. Well, you have no way of knowing that. If someone intercepts your communications and breaks it, you have no trace at all sometimes, most of the times. So it can be very critical because anything nowadays, pretty much anything important information that should remain private is encrypted. But sometimes if your cryptography gets broken, it can lead to disasters. So today we're gonna talk about four failures in the world of cryptography. They all have their own little names. The first one we're gonna have a look is called Linux Encoder 1, which is a computer virus, ransomware and cryptolocker that has emerged. It was the first Linux malware, first Linux ransomware. And so the other ones may ring a bell as well. Heartbleed was one of the major ones. So let's get started. Linux Encoder 1. So it's a ransomware. So basically something that encrypts your files and asks for a ransom to decrypt them. It was the first one on Linux, and it was very simple in terms of source code. We can we'll have a little look later and explain how it worked and how it was broken actually. So it didn't actually work very well because it was broken in only a few days. And to decrypt, well, it was in 2015, so one Bitcoin was worth way less than that. But I think it was around maybe 5,000 euros to get your files back. Let me move my head a bit. Nice. So first, we are gonna need to talk about some key concepts in cryptography. So the two words that I've provided here, so symmetric and asymmetric cryptography, they may ring a bell. You may very well know what those are, but let me just give you a quick recap. Symmetric cryptography, it's you use one key to encrypt the data, and you use the same key to decrypt the encrypted data. So the fact that it's called symmetric, it's because, well, you have a symmetry and it's the same key on both sides. It's something that's very fast, that's used very broadly. The main component of AES of symmetric cryptography is called AES. It's used very widely. The main example being HTTPS, which is based on that mostly. Asymmetric cryptography is kind of the same. It's based on more complex math. And this one, you have a set of two keys. Usually you keep one of them private and the other public. And so anyone who wants to send you information can use your public key to encrypt, and you use your own private key to decrypt. And otherwise, if you want to publish and authenticate a message to show that it's really you because you have the private key, you can encrypt using the private key, and anyone can verify that you were the one who encrypted it using the public key. And you may have already one of the two keys, and you can encrypt something with the public key. You cannot decrypt it using the public key. It's very important. So that way, any data that's encrypted using a public key cannot be decrypted unless you have the private key, the corresponding private key. Well, I think that's... take a time maybe to pause on the replay later and have a look at the slide. But that's the difference between symmetric and asymmetric. Asymmetric, you have two keys, two different keys. And symmetric, you have only one. So, how does a ransomware work? Well, that's a question that you may be asking yourselves, and that's a very interesting one. It's actually kind of simple once you have the concepts of symmetric and asymmetric cryptography. You can use pre-packaged source code to do all the operations. For example, I've used many times in my life cryptography, symmetric, asymmetric. There have been only very few times for very specific usages that I've re-implemented them myself. So you can already reuse packages and use stuff that has already been done very extensively by great people, because it's also dangerous to build your own cryptographic code. So pretty much all the ransomwares are the same. They use a combination of symmetric and asymmetric cryptography, and they use that to encrypt all your files. So we're gonna have an example, which is what a ransomware does, what a CryptoLocker does when it encrypts your files. So we're gonna take just a simple example with one file, and you can assume it's repeated on all the files on the system, for example. So first of all, we are gonna generate a random symmetric key. So it's only I think 16 bytes usually, which is the key that's going to be used to encrypt the files. This key, we're gonna use it to encrypt the victim's file system with that, and then we delete the originals. So if we have that symmetric key that's presented on the screen, we can decrypt, we can recover the files. Otherwise, it's completely impossible to recover without the key. That's the main principle of crypto. Then we're gonna do something, okay. Here's the little thing that's gonna be a bit complex. We take this key and we encrypt the key using the attacker's public key. So the attacker's public key, it's in the source code of the virus, and we're gonna use it to encrypt the key, the symmetric key. And then we have this key which is encrypted, and it's sent to the hacker, for example. Now what happens? We don't have, so the victim does not have the symmetric key to decrypt their files. And to get that key, you need to have the hacker's private key, which is something that only the hacker has. So if you want to decrypt, well, only the attacker can recover the symmetric key to recover the files. So you have to pay them to use their private key and give you back your decryption key. And so every decryption key is specific to one computer. So well, you cannot just buy the key for once and give it to everyone. So it's kind of a service of decrypting your own private key that's gonna allow, your own symmetric key that's gonna allow you to recover the files. Well, let's do some reverse engineering, if you will. It's an actual ransomware. The samples of the malware are quite easy to come by. I've downloaded them on a legit website, and so it's very easy to reverse engineer. Actually, it was it was the first Linux ransomware. So it's x64 ELF. It's compiled statically. Well, there's a lot of technical terms, but the conclusion, it's very easy to look at. So I'm using a software which is called a decompiler. We give it an executable file, so a compiled file, and it gives you back the C source code. Well, one possible C source code that we could have that could have generated that. So first of all, what the virus does is it opens the two files. So it opens the existing file plane, which is the plane, the raw file that it's going to encrypt, and it opens also another file which is the destination. At the start it's empty, but we're gonna write in that file. Then we generate a random key. So like I've shown you here, we generate a random symmetric key. It's right here, AES key. So see, we're using AES, and we generate 16 bytes. Function round string, we're gonna see a bit later what it does, what it is, but for now we generate 16 bytes of random data. And the same with IV. IV, it's another kind of key which is used to encrypt and decrypt data. The key and the IV are both necessary to encrypt and decrypt the data. Then we're gonna encrypt the key. So the first line, as you see, we encrypt the AES key with the hacker's public key. So that's exactly what I was mentioning earlier. And then we're gonna do a lot of file write operations to encrypt the file. This is another part of the core of the source code, which encrypts the file block by block. But this seems to be very well convincingly matching what I've shown you earlier while telling you this is how a ransomware works. So where's the bug and how was it broken? Well, the key, so the first line I'm showing you is part of the round string method I was mentioning earlier. We're using the round function, same as the IV generation. So every random data that's used is using rand, which is a built-in function in C, which generates random numbers. It's very, very easy. And in random number generation, we have a cool feature that's called seeds. So if you use the same seed for the random number generator, it's so if you use on two separate instances the same seed, it's gonna give you the exact same output values. So it's very important that, well, the seed that we choose is very random if we don't want somebody to be able to recover the data by just using the same seed as us. But actually, here in that ransomware, it's using time null, so it's using only the timestamp, so the number of seconds since January 1970. And so, well, now it's trivial to recover the seed because, well, you can only guess, you just have to guess at which second the attack was launched and recover what seed it was used, and then from that point on you can generate the exact same keys, and so you can decrypt the keys, the files as well. So recovering your files after being attacked, it becomes very trivial. You find when the attack started. Well, you only have to look at when the first encrypted file started, and you have that exact second which corresponds to the seed. sround, you initialized the random one of the random number generators on your side and set it with the attack start time, and then you can generate a lot of keys which are exactly the same as the ransomware generated, so you can recover the files that way. Okay, so this was the first attack. Now we're going to talk about, so this one was a bit special because it was a virus. Now we're going to have a look at kind of commercial products. To begin with, we're going to have a look at Safari, which is a browser implemented in a lot of Apple devices, especially iPhones, iPads, and Macs, sorry. So all devices were affected in 2014 by this bug, which was very critical. Actually, we're gonna see why, but it can completely break HTTPS. So, let me move again. So first, let's do a quick introduction to TLS. So what's TLS? TLS is a combination of, TLS is the S in HTTPS. So it's the way to secure HTTP connection. So every connection you do on the web that's secure with a little padlock, it's TLS behind that. It's used to be SSL, but now the new standard is TLS. And it's supposed to be secure against an interceptor, which is also called a man-in-the-middle attack. So anyone intercepting your connections should not be able to understand what's being transferred, and not decrypt at all. So HTTPS, there's something called the handshake and the protocol negotiation and everything like that before actually transferring the the encrypted HTTP data. First of all, there's the hello. So hi. So if my computer wants to connect to to google.com, you send the connection initialization. And Google replies, okay, hey, I'm Google, here's my certificate. And this certificate, it's signed, so there's actually a kind of a digital signature on that, which is delivered by something called the certificate authority. And if someone can prove their identity using a certificate, it actually is them. You can assume that. But actually, there was an issue with TLS for the case of Apple, which was that the certificate verification was not working properly, so anyone could make themselves look like they are anyone. So for example, you can very well steal the identity of Apple, of google.com by providing any certificate. So yeah, that's what I was telling. And then they say, okay, let's communicate using this key. Once you have authenticated the data, the server you're talking to, and then you use HTTP. You encrypt your HTTP using that key. So let's have a look at how the certificate verification was implemented inside Apple's Safari. So we have a lot of things, but what this function does, it computes the SHA-1, so a hash of the certificate, and then it can verify it using a signature, a digital signature. We're not gonna go too deep in that because the flow is much more high level than that. So as you can see here, it tries to do a lot of operations, and if that operation fails, so for example initialization of the hash and stuff like that, if that fails, it calls go to fail. So as we were saying, so as the name of the vulnerability is. And then fail is one last thing in that function, which just clears the buffers, frees the memory to avoid memory leaks, and then it returns the error code. The issue is right here, because we have twice go to fail that's written in the code. The line is duplicated, and I'm not sure how many of you are fluent in C, but if you don't use brackets after an if condition, well, it's only the next statement that counts as being in the if. So here it's interpreted as that. So the go to fail is always executed. And then the actual code, it's never checked. Where I've written a certificate is never checked. It's because this code is never reached, because we always go to fail, but the error code is 0. So the function returns correctly without even having checked the certificate. So this is kind of a big deal. So in practice, how we would use this attack is, well, you intercept the connection, pretend to be the server, so pretend to be google.com, for example, and you try to force, it was only in TLS 1.1, and not in 1.2, which was the widely used standard. But you can still force your, well, the person querying you to use TLS 1.1, and then you give them the wrong public key, not the Google's public key. That, well, that would be useless. You give them your own public key. So then the public key verification, it's never checked against the certificate, which was the point of that function, which was buggy. And then, well, you can pretend to be the server, and since you have the private key corresponding to the public key that's been provided to the user, well, you can decrypt that traffic and pretend that you are them. And so it was a kind of a very big deal at that time for every Apple user, because it was an attack that could be exploited on everyone and very hard to detect. So as I was saying, cryptographic failure can go unnoticed, and this one was one of the cases. So the fix was very easy. You just have to remove that one line, but it's still a very big flaw just due to one single line of code. And that's why code is very important in cryptography. Implementation is key, because in theory everything is already solved, but in practice we always have bugs like that lurking in the dark and waiting to be found by anyone, hopefully someone with good intentions. Heartbleed. Heartbleed was a flaw in Openssl Heartbeat. It affected a lot of servers, so about 20% of servers in the world were affected by this vulnerability, which allowed anyone to leak data from any server, so private data. TLS Heartbeat is just, it's a protocol. I'm going to be a bit faster because we're running out of time if I want to finish. Heartbeat is a way for a server to, for two computers to check that, well, one computer wants to check that the other is still connected, is still alive. So we send it a heartbeat. That's where the name comes from. So it sends some random data. Well, here I've written potato 123, and then the server will reply potato 123 to show it's still alive. So how this works? So this is the source code of Openssl, which is a very widely used cryptographic suite. So well, you can assume everything you use in cryptography uses Openssl in a way or another. So this is the source code. This is a struct in C. So as you can see, there's the type of the message. So it's either a query or a reply. So it's a Boolean. The payload length. So the payload is the thing, the potato 1, 2, 3 that I was mentioning earlier. Some implementations use different size payloads. So you use this. Then you have the payload, and then you have some padding, which is random data. So let's have a look at how the how the emitter can send the message. So how it's generated that packet. Then, it's then the struct is sent in a network packet. But first I made a little mistake in there. This is how the server which receives the packet parses it in variables and then writes the response in another part of the source code where the vulnerability is. So first we read the message type. Then we use this thing called N2S, which writes the payload length inside the object. So it's inside the object called P. And then we use we read the payload in there as well, so in the variable PL. And then the padding is discarded because we don't care about it. So now we have in variable HB type, we have the type, so which is query. We have also the payload length in variable named payload, and PL is the actual payload. Then how the response is written in another packet, well, it's quite simple. We write the type in the struct. Then we copy variable payload inside BP as well. So BP is the packet that's going to be sent back. Then we use a mem copy, so memory copy, which writes the amount of bytes specified in payload from PL. It writes it to BP. And then random padding, which is a random pseudo byte. So this is the actual source code of Openssl. The issue is that payload length is client provided and it's never checked. So we can give discrepancy in the values between payload length and the actual payload. So if we specify a very large number in payload length, the maximum being a bit above 65K because it's a 16-bit integer, but we provide a very small payload. In the response, the mem copy, the memory copy, is going to take a very large section of data, most of which does not belong to the original payload. So it's gonna send here, for example, this entire section of memory without checking that the only thing that we sent originally is the first only letter X, and so it can leak. So for example, here I've written a secret data of another user. It can be a lot of things, and if we repeat the attack a lot of times, we can leak a lot of information from that, because Openssl is used for many cryptographic things. So we can use that for a lot of well, it's used for a lot of other things, and so we can, for example, leak private keys to, well, do a lot of nefarious things. The patch was very simple. It's well, if we check if the payload length is more than the actual sent packet, well, we just discard it, return 0. We're gonna just skip over this part because we're lacking a bit of time. And thank you very much. Well, if you want to have a look at the part I've just skipped, you can send me an email, matis.hamel@sogeti.com. I'll be there for the live Q&A of the first session, I think. Maybe not on the second Sogeti's Got Talent session because it's quite a bit late in France. But otherwise, you can reach out to me via Twitter, or, well, anyways, you find me publicly. I'll be reachable. Thank you very much. I hope you enjoyed the session, and, well, I wish you a very good day.